All right, good morning, everyone. Still morning, not 12 o'clock, and I'm the one standing between you and your lunch. So I'll make sure I'll try to make it as attractive as I can. To begin, my name is Anurag Bhargava. I'm Customer Success Manager at Keysight, supporting various customers, various applications. Some of you might find my voice little familiar because I create a lot of YouTube videos, post on my YouTube channel. And it's not only about ADS, it's actually mostly covers all the different tools which Keysight has, ADS, System View, and so on. Now, before we begin today's presentation, just a quick check. Is anybody involved in doing RF modules here or looking to do RF module kind of applications? Pretty good. And those of you who are not yet doing it, basically will pretty soon, start doing it because that's where the future is. Especially when we think about our systems getting, smaller and smaller and lightweight. Idea is to integrate as much as we can to achieve the best performance in the least amount of space which can handle. So today's presentation, we will explore a typical RF module. What are the challenges in terms of design, simulation, as well as assembly? So I created a very simple dual band RF module, which we will walk through, but still capturing all the key difficulties which designer face in order to come out with a product in the market. Right, and reason again, like Nilesh, pointed out in the beginning of our session today, is all about shifting left. And shifting left can be defined in many ways in design manner. If you can reduce your prototyping stage to a minimum, do more things in simulation, doing it earlier than what you typically do will help you. And this entire thing, if you look at where we are headed, a lot of different applications are basically driving the need to go to higher frequencies, which in turn means more complex systems. Because in the previous days you had one function out of one particular IC or system which you do. Now it's all multifunctional with many bands included into a very small form factor. So those challenges are taking us towards doing things in a new manner. Heterogeneous integration is the buzzword. How do you integrate all those different varying technologies into the same kind of module or a package? So everything is bringing a lot of interesting challenges as we go along, and I will try to answer those. Now, if you think about 5-10 years ago, when you are doing relatively simpler systems, when I say relatively, doesn't mean it was simple at that time when you're doing it, but if you look back from now, there were far more simpler systems 10 years ago than what we are doing today and what the future is bringing in terms of 6G, autonomous driving and whatnot. So in the past, you were able to survive by having, few things which are essentially designed in isolation. You could have different teams doing, different kind of stuff in their own silos. And the integration used to typically happen towards the end when each of these pieces are ready. You try to integrate, you try to test. And at that point, if you have a problem, then you open a can of worms because it could lead to fights between different teams whose system is not working and why, and who's the culprit of system not being working and so on. So that process is still used to work, but the way technology is moving, it's already unsustainable if you approach the product design in that manner. So you would need more integrated system. You need to do things much earlier. You somehow need to find a way to bring multiple technologies together to be simulated, analyzed, and then you can fine tune the overall performance. And that's the whole scope of this presentation, giving you some direction, how can we achieve that. Now, we as a company, in fact, also face similar challenge when we develop our own instruments and all those very high frequency terahertz communication. So here is just an example of an internal success story which we had deploying the technique I'm going to talk about in our own product design. So what you see here is a UXR series oscilloscope. It's a millimeter wave oscilloscope. And the way we used to do this front end design is something shown here in the picture. And as you can see, it's kind of very typical to how previously systems were designed. You had all these different pieces, and then you connect them using these thin film circuits or thin film lines and so on. So that was okay, but it was not giving the performance when Keysight was thinking how to extend the frequency range of this instrument. That became the bottleneck. The front end became the bottleneck because it wasn't allowing us to get the lesser loss with a better performance at higher frequencies. So what our labs people came about is to change the whole design methodology. So we shifted from hybrid kind of front end to wafer level packaging front end. And you can see the difference between these two. But once you go to technologies like WLP or wafer level packaging, it brings out another challenge, how to control the parasitics, how to design things, because life was much simpler here because everybody does their job and finally you bring it together. But now once you have more integration done inside a single module or a package, then it brings out another challenge. So using some of the things I'm going to talk about today, they were able to leverage a lot of these integration, doing things what usually was done at the end of the product design much earlier in the process, and integrate multiple technologies together and analyze all the critical RF paths and achieve and fine-tune the performance. Now, sometime when you think about packaging, packaging we all know brings out a lot of parasitics into action. And usually parasitics are undesired element. It's like harmonics in your design or intermodulation product. But if you are analyzing things at a much deeper level, we can use those parasitics to our advantage. So instead of becoming an undesired element, they become part of our design process. So if we know there will be certain amount of parasitics, no matter what you do, we can absorb that as one of the design elements and fine-tune overall performance to make sure parasitics works in our favor rather than against us. And that's what we were able to achieve. And here, if you see the performance, although kind of difficult to see from the back, but we achieved almost like 20 dB isolation, which is much better in the wafer level packaging, kind of concept. And also, if you look at the loss, which we were able to reduce right at the higher frequency, this blue curve here shows much less loss than what the traditional, style of design was doing. So this allowed us to extend the frequency range of the front end of our oscilloscope and come out with a new product in the market. So success story like these, better design techniques, tweaking your design flow with the existing tool you have, but change the slight methodology, you can extend the range of your products to be much better. So as I said, the case study I have here is a typical dual and band module, and we will go through 4 of the key challenges. There are more challenges, but due to time available, we'll focus on 4 key challenges. Starting with technology assembly, doing the multi-technology circuit design and analysis, talking about how do we approach the electromagnetic analysis, because denser the things get, EM analysis becomes more and more important to make sure there are no undesired coupling, there is no undesired impact which one system is having on another. And then finally, putting it all together and optimize the overall product level design. Now, I'm going to focus more on ADS. I'm kind of assuming everybody here knows about ADS. It's been there for many, many years in the market. And it's a great platform to do such technology. The reason for that is, no matter which technology domain you are working, so if you think about typical IC design tools, you have 3 key IC design tools. You have Cadence, you have Synopsys, you have ADS. Now, Cadence, Synopsys more focus on CMOS and BiCMOS and those kind of processes. ADS more focuses on GaN and GaAs, which we typically call as 3-5 semiconductor. So no matter which domain you are working with, you can bring in those designs over to ADS, because most of these tools are open access. They share the same database structure as we do. So it's easy to bring those design and getting ported over to ADS. Now, in terms of package, you may have your own package design tool like APD, SIP. In fact, ADS is a very great package design tool now. So any of those design formats can be easily ported over to ADS, and we can perform the whole technology assembly, and then we can go to simulation, whether it's a circuit simulation, electromagnetic simulation, or electro-thermal simulation. So all kind of multi-physics simulations can be employed there. So if you look at in a simplistic manner, and my next few minutes will be focused on these 3 key main pillars. We start talking about integration. How can we bring all these multiple technologies together? And then we talk about assembly, which is mainly focused towards layout assembly. How do we put together all these diverse technologies together in a common layout, like how it will be fabricated. And then finally, we'll talk about simulation. It could be circuit simulation, system level simulation, or electromagnetic simulation. So I'll keep on referring to these 3 pillars as I go along, and I will have the right snapshots at the right places so that you can see what I'm talking about. All right, so, sorry. I'm almost shouting. All right, I'll try harder. All right.
Really quick.
Yes, please.
So for this wafer level packaging, which tool is used for this?
ADS and few others, yeah, non-Keysight tools as well.
Can we download?
Can you, sorry? This database which I'm going to show you, is that?
The software. Can you download?
Software, yes. I will have all those instructions. You can download the software to try. The demo database which I'm going to present today is also available. If you need the database I'm going to show you, just make sure you mention in your feedback form, and we will send you a link to download all the collateral, all the ADS workspace which I'm going to present today. Right? It's all my design, so no IP. I don't need to take anybody's permission, right? So it's freely available. All right, so we'll take a look at that demo example. I'll go through some of these key topics along the way. And again, somebody asked about evaluation. If the messaging sounds interesting to you, you can take a picture of this slide. It will not be in the link which you download, or you can of course go to keysight.com and apply for the trial. And this link will directly take you to the trial page. You can request the trial as you want. I'll give you a few seconds if somebody is taking picture.
Is that RFPro?
Yeah, that's RFPro snapshot, but the trial will be for ADS. RFPro is fully integrated inside ADS, so yep. All right, so let's move on. I will have that snapshot again. So let's talk about first challenge. If I'm doing such a module and I have different ICs, different schematic, different technology, it could be GaN, GaAs, it could be CMOS, it could be other technologies. How do I bring all of these different schematics together to simulate the system at a circuit level? We'll talk about layout and EM later, but that's the first challenge you face. Now, ADS as a platform has a very unique concept called workspace. Now, inside a workspace, you can have many, many libraries. Each library can have its own technology, its own layer definitions, and so on and so forth. So if you are doing a native ADS design, and let's say your all IC teams are using ADS, good for Keysight, but that's not the reality. So people use in real life Synopsys, Cadence, and so on. So if you're doing your IC designs in Cadence that you want to bring over to ADS so that you can combine it with ADS design, it can be easily done if you have an interoperable PDKs, if you have IPDKs, Or if you don't have those, if you are working on native, Virtuoso, or Spectre PDK, you can use Cadence Dynamic Link, which we have for many years now. And you can bring in all those IPs inside ADS, assemble all that, and then you can perform your linear, nonlinear, time domain, those kind of simulations. So it makes it really very easy. So at this point, enough of PPT. You have been seeing PPT since morning. Let's get down to action. When we have the tool, why not use it? All right, so here is that workspace, which again I can send you once you mention it in the feedback form. So here in ADS under Design Kit, if you look at Manage Libraries, I already have few libraries loaded. Now notice these libraries can be coming from third-party tools, as well as it could be part of ADS. And if you want to bring in any external library, the process is kind of pretty simple. You simply click on this button called Add Library, browse to the location where your library is. Like in this case, I would like to bring in this board level filter library to be added to my overall module space. Simply click OK. And now that library is added, and I can access that library and the rest of the designs in this library. Now, once you have this all added up into your workspace, you can start to design a schematic. For example, here I can right click and create a new schematic, give it whatever name you want. And now, since every database is available already here, I can go to, let's say, this mmWave 5G amplifier design. I can simply drag and drop that piece that brings a 5G amplifier. Now, if I push inside this amplifier, you have the whole circuit level design following a particular PDK, right? So that PDK can be added as well. In this case, in this workspace is already added. But here you can see you can get down to transistor. You can look at all the design kit elements and so on. Okay. So then we can push out, and again here I do have an LTCC filter. For example, this has been simulated or measured. I have the relevant file. I can simply drag and drop. So using the simple process of drag and drop, you can combine these multiple pieces, and you can come up with an overall module schematic integration like shown in this picture. So here I have a 4G amplifier, that's 5G amplifier, SPDT switch. So all these three are my MMICs being designed with GAS technology. I have LTCC filter at the 4G output. I have another LTCC at the 5G output, and then remaining the off-chip components. So this entirety is my dual band RF module schematic representation. And again, for simulation, I can either run S parameter, harmonic balance, circuit envelope, all these kind of modulations, and perform the analysis of this overall module. And again, moving on, this is just a quick glimpse. So we continue our rest of the discussion. So that was how easy it was to bring in multiple schematics, add it up in your workspace, and design your circuit. Now let's go to another pillar which we talked about, is about assembly. Okay, the circuit level designs are analyzed, optimized, tuned. So now you are all set. Now once you have done your modifications, you gave this information to your layout guy, and he's ready with all the layouts. And now you need to assemble all these layout pieces together to create the full module artwork. And again, in this picture, you can see that's my LTCC of 4G, that's LTCC filter for 5G. This is a flip chip amplifier, which is mounted on this module. This is a 4G amplifier, which is wire bond. This is a SPDT switch, which is going to be wire bonded. Now, IC is one part of the problem. So you have the 6-layer laminate on which you are mounting these ICs and LTCCs. Another key aspect, which is very important in such dense module packages, is your SMT components. Because once you start placing SMT components very close to each other, especially inductors, you may have a magnetic coupling between those inductors. So traditional way of doing designs for all these components is to simply use the vendor supplied, circuit models, right? But in case of modules, that's not sufficient. Well, you can of course do that. That's a good starting point. You would really like to have the 3D models of these SMT components and really simulate those 3D model. That will allow you to capture the coupling between elements. A 3D model of SMT might be coupling with your IC because there will be always a fringing field, and if they are placed very close to each other, you may have all sorts of couplings here, right? So then our platform is also ready to get these vendor 3D models and get included. Now, vendors like TDK, Murata, and few others, if you request them, they can give you a 3D encrypted or unencrypted models for their components so that you can bring into your ADS design and even integrate that. So in my next demo, I will show you some examples of how these models. Traditionally, if you think about when you talk to these vendors, they give you encrypted model in a third-party format, which is namely HFSS right now. And now they have started giving out ADS compatible 3D encrypted models as well. So if you ask them, they will give you, they won't upfront publicize it on their website, but if you reach out to them, they will be ready to offer such models. If you face any troubles, you can of course contact Keysight. Sorry, question?
Can you use HFSS model for the slide?
If it is an unencrypted HFSS model, yes. If it is an encrypted HFSS model, then only HFSS can decrypt it. But anybody having, I work with few customers who have their own set of HFSS library, which is unencrypted because it's their internal model. We provide a Python script to do a batch translation from HFSS to ADS conversion. And once it is in our format, you can easily use it. And same script we also provide to vendors who are providing such libraries to their customers. Question?
Is your format encrypted also?
Sorry, come again?
Is your format or your model encrypted?
It can be encrypted, it can be unencrypted. Yes. So we do have our own encryption like HFSS has, which our tool will be able to decrypt when you run simulation on. Okay. All right. Okay, so that's the second piece. And ADS, as I said, in last few years, ADS layout has come of age. Lots and lots of improvement has happened in ADS layout, especially for IC, which is more focused on 3.5, as well as package design. Now, ADS is one of the very potent, package design tools. So a lot of improvements have been done, and it provides a lot of useful information. So that's about routing. But then when you're bringing all these form factors, let's say your IC is in Virtuoso, doing your silicon process design using maybe Global Foundry or TSMC kind of process. There are few ICs being done with GAS and GaN technology. There's something with LTCC. How are you going to assemble all these? Because everything has its own technology stack. Everything has its own form factor. And again, in ADS, the heart of this whole thing is SmartMount. A SmartMount feature in ADS makes assembly job piece of cake compared to what you were doing earlier. Earlier, if you had to do something similar, you need to come up with a composite stack, and it is nightmare to manage. Because if it is only Z-axis, what you are worried about, no problem. You can always build a composite stack. Let's say starting from PCB, you add the module layers, you add the IC layer, and then you have one composite stack. But in these cases, your ICs are sitting side by side. So as soon as you have X and Y, you cannot manage a composite stack because two layers cannot coexist at the same interface. It has to be only one layer at one side. And that's what typically SmartMount feature in ADS allows you to do. As you can see, ICs are sitting side by side on a laminate with the balls sitting on a PCB. It doesn't make a difference. That's the beauty of this. So it's very simple, very powerful, versatile. And I will show you all this in live action once I go to the demo part. All right. And not to forget, ADS also has a range of verification tools, things like LVS, DRC, LVL, ERC, all these verifications are supported. And the good news is you don't need to pay extra money to have LVS or DRC. They are all part of ADS layout. So making your economy works better for your company. All right. So all the verification tools. And another beauty is most of the tools, if you think about in LVS DRC, they are IC focused tools. So you have Caliber, you have Assura, you have other LVS and DRC, but they all focus on IC. But here you are not doing IC design, you are doing module design. So you have IC, you have laminate, and you have ICs of different flavors. How are you going to do LVS? How are you going to do DRC? It's a 3D DRC, right? It's no longer a normal 2D DRC. So ADS DRC tool has features for both IC, module. It can do multi-technology, LVS and DRC. So that's another benefit of you adopting ADS platform. All right, so enough of PPT. Let's go down to demo and we talk about how can we put all of these together. Okay, in the same ADS workspace, which I opened, here you can see I have different libraries included, which I gave you a brief introduction before. Now, each of these libraries, if I open MMIC, here you can see it has its own technology substrate. It has its own technology information. And similarly, all the other libraries can have their own respective technology, their own stack-ups. So how do we bring it all together? So let me go ahead and create a new layout. So that's my laminate library, which I'm working on. And I will simply create a layout. Now, in this laminate, I have my laminate layer technology. It's a 6-layer laminate technology. And you can see I have a placeholder for a bump and a bottom cover plate. Now, if you had a PCB below that, you could have a separate PCB technology or PCB and laminate into one technology. It's up to you how you want to manage. Now, if I have to assemble, I need to first get a laminate design. So for example, here I have a laminate board. I can place it into this technology. No confusion, because now this is the same technology which we refer to, right? And here you can see some white outlines. Those are placeholders to place various ICs, 3D components. Now, each of these libraries have to be mounted in a specific manner. So I want to place this 5G amplifier. So you could either do a flip chip mounting, or you can do a bottom mount mounting and then use a bond wire to assemble. So how does I tell ADS that this design, when I place it on this laminate, have to be flip chipped, right? So simple. Let's look at a smart mount. We right click, go to technology, look at nested technology. And here you can see I have a smart mount. And here you have various type of smart mounts, bottom mount, flip chip, and so on. So I define this IC to be a flip chip. This is how it has to be assembled. As simple as that. Couple of clicks and you have assigned that IC to be configured as flip chip. Now, when I bring that IC and I would like to place on this laminate board, for example, so if I push in, and let me delete this IC, which was already placed there. Okay. So I come back to my top level design, and that's the placeholder for my flip chip IC. And this is where I would like to place it. So I can simply go to this IC, open up this cell, drag and drop that layout over to this laminate. Now, key thing you notice on the bottom right-hand side, the laminate is being designed in millimeter, technology. It has all preferences set for millimeter. But when I dragged and dropped that IC, and if I open the layout of IC, if you refer to the lower right, it's micron, right? And usually all ICs are micron. But when I drag and drop that IC, it retained its technology. It retains its units. It doesn't blow out of proportion to scale as per mm. It retained everything. And here, if I zoom in a little bit, you can also notice the IC is flipped. Now let me open it side by side so that you can get a better sense. So let's put this IC on the side and let's put here. So what you see here, although let me switch off few of these windows here. All right, so what you see here on the left hand side, and let me try to bring it a little on the right here. So what you see, can you see it's flipped, right? It's flipped because I marked this library that I'm going to use a flip chip. So when I drag and dropped it onto laminate, you can see this portion and you can see that portion. That's kind of flipped. Okay. Yes, question?
Top layer has bumps inside the definition you have seen.
Yes.
So those
Bumps are now going to be mounted, and I'll show you a 3D assembly picture so that you get a better idea. All right. And another nice thing is the stack up of this IC will, when I go to EM analysis, it will also be flipped automatically. You don't need to manually create a flipped stack up so that you can do a composite stack. Once you mark this as a flip chip smart mount, everything else will be taken care by ADS. You don't need to bother. Again, the idea is not to cause extra work on designer. Plus, you don't need to maintain 5 copies of your stack up, one in bottom mount, one in flip chip, one is rotated, and so on and so forth. So once you mark the signature, rest everything is taken care by ADS. Now here for this IC, I need to mount it on this design. Let me rotate it. That's how the footprint is created. And now I can simply press M to move, pick up one of these pads, and then I can go to the respective location in my laminate, and that's where I'm going to place it. So again, would you believe you already did a multi-technology integration? You have the laminate, you flip the IC, you mounted it on the laminate. This is 2D view, so probably not very clear. So let's go and look at a 3D view of this assembly which we just created. And while 3D view is opening, there's another key thing which I will also talk about in a moment. So here you can see the laminate and the flip chip IC. You can see the integration pad there, or the via. It could be bumps, it could be any technology which you create. So that's the quick assembly we are able to create. And I'm not joking when I say, if you try it out on your own database, it is exactly what you will get. It is as easy as you are seeing it. Because sometimes I have seen designers, they've been struggling so hard to do such assemblies. When they first see it, they don't believe it. They say, no, there's something wrong here. But it's no marketing gimmick. This is how it works in real life. And I invite you to try it out on your own database if you have. Or once I send you this database, you can try it out yourself. For this database, we have a step-by-step workshop slides also to guide you on how to navigate through the entire thing. So that also I will be sharing along with this demo if you want. Okay, so that's the IC integration. Now let's talk about 3D components, which I mentioned. So here, like any other IC technology library, I also have this spatial library, which we call as mmPro. Now mmPro, if you know, is our equivalent of HFSS. It has the 3D modeling interface, and that's the format vendor will give you the ADS library in. Now each of these cells which you are seeing here is actually a 3D component. And if I open one of these library component, you can see there's an mmPro view, and I can open up this 3D model. Now I'm able to see the 3D model because it's an unencrypted component. And now here you can see this is a 3D model for an inductor, which is how, if you have not anytime cracked your SMT inductor and looked under microscope, this is how internals of your any SMD inductor looks like. So you have those windings, and it is offering certain inductance. So once you have it, now if you have your own third party like HFSS file, you can see it has HFSS import option. Using this option here, you can refer to .a3d comp file you have or .aedt file you have and the associated SAT file. So you can very quickly translate any HFSS model into a 3D model, which you can use inside ADS as well. So if you have HFSS, you can go ahead and bring it over. Once you have it, simply save it and add it into ADS, and that becomes your 3D component library. I have similar customers who also do things like package modeling or the shield modeling. So they have 3D shields. You simply import that, and EMPro can import from all mechanical CAD tools like SAT, SAB, IGS, all kind of files. And then you can simply save it and add it as a library in ADS. Sorry, yes?
So if you're putting a shield around this module,
you can if you want. Yes. So because a lot of time when you put shield on top of module performance can change, and you can actually model all that by just building a 3D model of the shield, putting it on your laminate or the yes, molding, correct. Okay, all right, so let's moving on. So using the same technique, I have assigned different libraries. For example, this LTE, amplifier is mounted as bottom mount. You have switch. If I look at switch library, that has been defined to be mounted as bottom mount as well. So once you have all these pieces, let me show you a final piece which you will be able to do at your own side. So here is the layout assembly for fully populated module. And if I open up our RFPro, which is going to be my last topic. So how much time do I have? 10 minutes? 5 minutes? 5 minutes? Okay. I'll try to speed it up. But again, since time has its own restrictions, if any of these things you would like to discuss in more detail, either me or one of my colleagues can have more detailed discussion. So here is the picture which you saw. That's the module. You can see you have 3D components. You have wire bonded IC for the 4G amplifier, and also for the SPDT switch here. And then also this is the same flip chip amplifier which I talked about earlier there. Okay. Now when you have all these things here, you have all the layers stack up, all the dielectrics, all the material properties automatically brought into simulation environment. So if you look at the stack up, and if I expand it a little more, and here you can see dielectrics. Can you see this MMIC? So that's a stack up for all layers of dielectric in MMIC design. This is the SPDT switch dielectric. That's the 5G dielectric, and that's the laminate dielectric. So when you mark it as a smart mount, you did your layout, you open it up for analysis, all the stack ups of all those individual pieces are already called, assembled as how it should be in real life. So again, from designer's perspective, you don't need to put in any extra effort to create a composite stack or how do I manage this stack. Everything will be done by the tool behind the scenes. So least problem for designers, and no excuse for not doing such analysis when you have that feature available, right? So why wait to integrate all this piece and test and then find out that matching somewhere was not okay, one thing is interfering with another. You can actually simulate it, reduce the number of prototypes of failures which you have, and then you can proceed. Another cool feature of this interface is, let's say you assemble this piece, but before you commit to a full-blown 3D EM analysis of this module, what if you would like to see, so let me actually put that in a wire frame. What if you would like to see, there are a couple of traces, critical traces. Like for example, let me put it on top view mode here. So let's say I have, this 4G trace and I have this 5G trace, right? And they are pretty close to each other. And there might be, some coupling between these traces. So before you go on to full-blown simulation, you may just want to pick up this track and this track, and you would just like to analyze it. In traditional tools, what do you have to do? You have to cookie cut your layout, you have to remove everything, and then only you simulate. The beauty here is you don't need to do it. We don't touch your layout. We don't ask you to save n number of copies. I can go to the nets. See, once you read the database, you have all the nets here, right? So I pick up this net, and I can pick up another net, which I would like to analyze. For example, these two nets I picked up, I can right click and create something called user defined EM, and I can put both of these nets here in the analysis. And I can bring in my ground into the picture. And now I can take these two nets, let me turn them into signal, and I can right click and create a port on these nets automatically. And now your entire analysis is set up. So if I highlight, that's what you just set up. Out of this huge design, I only picked up my selective nets. I can add it into analysis, and now I can go ahead and set up my simulation by double clicking, going to options, set up your frequency, choose your simulator. I would rather prefer a full 3D FEM, which is integrated. I can run a local simulation, or I can send it to cloud or LSF, which you may have. You can run parallel frequency jobs, let's say 2 parallel jobs, 4 parallel jobs, to reduce the overall simulation time, and you will be up and running. The simulator internally will do the cookie cutting for you. It will limit the solution without changing your layout, without you doing the extra work. All that work, you're spending so much of money of buying these advanced tools. Let tools do the work. Why designers do the work? All right. Okay, so these are all nice features inside for doing such designs. So just quickly wrapping off for the last section, I already touched upon simulation a little bit, but you do have a nice, RFPro, which I just demonstrated, which is one cockpit to do either a planar EM or do a full 3D EM for any range of problems you're solving. It could be a simple board design, it could be an IC design, it could be an module design. One tool can handle different range of problems which you have. Like in this case, for example, I simulated this entire module. I used a single machine. It took like 9 hours to run on a very simple, i7 processor kind of machine. But same time, I did a 4 parallel jobs. The whole module with all ICs, 3D components, I was able to simulate in around 2 hours, right? So that's the power of parallel simulation. It could be your internal cloud, LSF, or external cloud like AWS, Azure, depending upon what you have in your company. And once simulation is done, what is another challenge which you face in a typical tool like this? Whenever you run any EM simulation, your diodes, your MIM caps, your transistors all have to be removed from EM simulation. And people manually place ports at all the pins. It usually ends up in 200 plus ports for a typical module. Even for IC level, if you think about your CMOS IC or SIGI IC, you easily have 100 ports. If you remove all devices, you connect ports. So as a designer, first you remove all of them, you manually put all the ports, you run simulation, okay, you end up with 100 port, 200 port S matrix. Eventually, this S matrix needs to be recombined with the remaining discrete components which you have, like transistor diodes. So manually, you sit down and you wire each of these up. Imagine how much time is needed for 100, 200 connections. And it's very easy to make one wrong connection. And once you do that, you simulate, performance is not meeting, you tend to troubleshoot, you spend a lot of time. Another nice advantage of RFPro, when you do such things, you are doing the entire partitioning in the tool. Tool keeps track of this connectivity. So when you create a schematic, it auto-populates your EM block, your circuit blocks, and the connections in between. So again, as a user, you have zero chance of error. As long as your layout database was perfect, the resulting schematic will come out perfect. You don't need to spend any time. And then you have this module ready. You go ahead and run, linear, nonlinear, modulated, whatever analysis. Again, so that's some plots for this module result. And again, for modulation, you have various techniques like virtual test bench. This is like having Keysight signal source as well as signal analyzer in your tool to do full-blown modulation analysis. Or you could do something like compact test signal, which Murthy was talking about. Instead of simulating a whole frame, you can take a small segment of that waveform, which is statistically correct, and you can run modulation analysis, capture EVM, ACPR, and so on. These simulation runs in a fraction of time rather than hours of simulation. Okay? And lastly, not to forget, electro-thermal, because thermal performance is also a key in these kind of module designs. An ADS electro-thermal simulator is okay to run either on a simple IC level simulation, or you can do it on a multi-technology basis like the module which I have shown, as long as you have the thermal information for each of those processes. All right, that's my last slide. In case you missed to click the picture in the beginning, you still have chance to take a picture or scan the QR code and you can apply for your trial. So that's all from my side. Thanks for your attention. I know everybody will be hungry, so let's break for lunch. And I'm still around in case you want to discuss anything with me over lunch. I'm here. We can have a discussion. Thank you very much.